So this lecture is on mass and weight. So you've probably know that there's a difference between mass and weight. Um, Weight is when you measure your weight, you measure it in pounds usually. Your mass is measured in kilograms. But what you might not know so much about is that weight, pounds is actually a unit of force, and weight can also be measured in units of force like newtons. So the definition of mass is listed here. It's the quantity of matter in an object. Mass is constant. It only changes if the quantity of matter changes, and it's measured using a balance. Now, why would you need to use a balance to measure mass? Well, you could, if you used a weight scale. The difference between how a weight scale measures weight and how a balance measures mass can be thought of with the idea of a comparison. So you might have been in a doctor's office where they use a balance, and they have you stand on top of the balance, and they counter your weight with a known mass. If the weight that you apply to the balance is equal to the weight that the known mass applies, then we can say that your mass is equal to that mass. If you were on a force scale, which is measures just the force that you're applying, well, depending on where you are on Earth, your mass would be, your measurement that they give would be different. The weight would be different. So they can't say what your mass is. They can only say what your weight is at that location. Take it to the extreme. If you were standing on a force scale on Earth, you would be given a weight. And if you went to the moon and stood on that same scale, your weight would be 1/6 less of what it is when you were on Earth. But if you stood on a balance on Earth and you countered your the weight that you apply, the force that you apply to the balance with a known mass, your mass can be determined. If you go to the moon, now your mass hasn't changed, but the weight that you apply to the balance changes. The mass that's used to counteract your weight, it doesn't change because that mass is experiencing the same weight. So that's how a balance is used. That's why a balance is used for mass. So again, weight, it's the measure of the force of gravity acting on an object. It varies with the magnitude of g. So depending on where you are on Earth, your weight could change. Depending on what planet you're on, your weight changes. It's measured using a spring scale or a force sensor. So here it says, suppose you want to make some money by purchasing precious materials such as gold at one altitude and selling them for the same price in dollars per newton at another. Describe the conditions that would favor your buy high, sell low strategy. So this is an interesting idea. When you're selling precious metals, they do use a balance because they know that depending on where you are, the weight of the materials would be different. So if you went to a very high altitude, or if you went to the North Pole, for example, where you have if you went to the equator where you have a higher or lower value of g, you can buy your materials, your precious metals, for less money. And then if you went to a lower altitude, or if you went to the North Pole or the South Pole where the g is higher, you'd be able to sell them for more money. Number 2 here, it says an astronaut on the surface of Mars finds that a rock accelerates at a magnitude of 3.6 meters per second squared when it's dropped. The astronaut also finds that a force scale reads 180 newtons when the astronaut steps on it. What is the astronaut's mass determined on the surface of Mars? So here, I think I'll just pull up the calculator for this. We are basically just looking at F equals ma, or F equals mg. The force applied is 180, divided by the acceleration, which is 3.6. We end up with 50. So that is the person's mass, 50 kilograms. What should a force scale read if the astronaut stepped on that force scale on Earth? Well, we know the astronaut's mass is 50. If they step on a force scale at Earth, we just have to multiply that by 9.8, and we get 490. Next question. A 500-gram mass is hung on a force scale at a location where the magnitude of the gravitational field strength is 9.8 newtons per kilogram. But the scale's reading 4.7, so it should read 4.9. What could be a problem with this? Well, if the scale isn't calibrated properly, it might have an error. So the title of this slide is Free Fall, Weightlessness, and Microgravity. And we're going to talk about these three concepts. It says here, astronauts aboard the International Space Station experience a sensation often referred to as weightlessness or microgravity while on the station orbiting Earth. However, the terms weightlessness and microgravity are misleading because they do not explain what is really happening. So at the altitude the space station orbits Earth, the force of gravity acting on the astronauts and the station is about 90% of what it is at the Earth's surface. With such a large force, microgravity or weightlessness are not good descriptors. So when you're up in orbit where the space station would be, you're still experiencing the force of gravity. It's actually pretty significant. It's 90% of what it is at the surface of Earth. So it's basically 90% of 9.8. So why is it that there's this experience of weightlessness, this microgravity that is kind of that we see astronauts sort of floating around in the space station? Well, here's an idea that Isaac Newton proposed. Let's say you had a very tall mountain and you shot a cannon around off of that mountain. Well, the cannonball that falls is going to kind of curve back towards Earth. But if you shoot it fast enough, it could never curve back down towards Earth, and it could just go around in a circle forever. That's the idea behind orbiting satellites around the Earth. So the cannonball kind of would always be sort of curved downwards, but it would never actually hit Earth. This slide further explains it. So it says here, the idea of this cannonball going around the Earth is much like this idea of the space station going around Earth. The space station and everything inside of it, they experience this accelerated motion just as this cannonball would. So notice again, or remember again from our first unit, when you have circular motion, there is an acceleration because we have a direction change. So when you jump from a height to the ground, you momentarily experience free fall. So that moment where you jump up and then you start to slow down, and then you start to fall. That's that free fall experience, right? It says virtually no force is acting upward on you as the force of gravity pulls you down toward Earth. However, the time interval is so short that the sensation does not have time to take effect. The interval of free fall or weightlessness is extended for astronauts during training. So, in a situation where you can artificially create free fall, you may have heard something about airplanes that take parabolic flights up and down. Well, as they make that parabolic curved turn, you would experience an effect of weightlessness for a significant enough amount of time that you would actually kind of feel like you're floating in air. And this is actually where it explains it here. It says astronauts are placed in the cargo hold of a large military transport plane. The planes climb to a high altitude, then it dives to gain speed, and then it pulls into a large parabolic path and into a dive. So during that upper part of the parabolic path, the plane's in free fall for about 30 seconds. So astronauts float around and they experience that sensation of weightlessness. Here is a slide to copy down. Weightlessness or microgravity. The terms often used to describe falling objects. They're misleading because gravity is still in effect. A better explanation is that the object is experiencing constant free fall effect. So that space station that goes around Earth, the International Space Station, it's at a point where the astronauts are constantly experiencing free fall. Just like the cannonball going around the Earth, it's accelerating, and the direction of the force applying its acceleration is pointing towards Earth. It's almost as if it could fall at any time. So it's actually, while it's going around Earth, it's in a free fall effect as well. It's in that free fall situation. And that's the same thing that happens with the International Space Station. So here's a relatively easy question here. It says a 74-kilogram astronaut goes up to the International Space Station on a mission. The gravitational field strength is 8.6 newtons per kilogram on the space station. So what is his mass? Well, his mass won't change. It will be 74 kilograms. What is the difference between the astronaut's weight on the Earth's surface and their weight on the space station? Well, this one here we can solve using our calculator. So the difference between 9.8 and 8.6 is 1.2. So we multiply that by 74, and we get 88.8 or 89 newtons if we round for significant digits. Weight depends on g, whereas, oh sorry, I should read the question first. Why does the weight of the astronaut change but not their mass? Well, because weight depends on g, whereas mass is a quantity of matter, and it's constant wherever you are in the universe. Again, why is the astronaut appearing weightless on the space station if they have a weight? It's because they're in a constant free fall effect. Question 5 says, we have a 24-kilogram object that sits on top of a scale calibrated in newtons. Determine the reading on the scale to 3 significant digits. So normally we would do it just to 2 because we were given 2 significant digits. Here they're saying do it to 3 significant digits. So when the object is at rest and no one is pushing on it. So in this case, we have an object that is 24 kilograms. It is only experiencing force due to gravity, so we multiply that by 9.8, and we get 235. The next part of this question says, if somebody's pushing down on it with a force of 52 newtons, well, we would take that answer and we would add 52 to it, and we get 287. Let's see here. So what about if the object's at rest and somebody's pulling up on it with a force of 74? Well, let me get rid of that 52 just a second. So I'm going to subtract the 52 that we had before. We're back to 235. Now we have to subtract 74, and we get 161 newtons. That would be the force that we see. And we're done.